This demonstration will be solving problem 6-121. The problem states, determine the couple moment M that must be applied to member DC for equilibrium of the quick return mechanism. Express the result in terms of the angles phi and theta, dimension L, and the applied force P, which should be changed in the figure and instead directed horizontally to the right. The block at C is confined to slide within the member of slot AB. So there are a couple of things that we need to watch out for in this problem. First one being this block C at point C. That, since it is this block that's confined within the channel, has a normal force that acts on each bar, and that can only be directed perpendicular to the line AB. The second one is, if we are going to relate the normal force between the bar AB and CD, we're going to have to find this length x right in here between A and C, so that we can find the length of that moment arm. So here we have a simplified diagram of how we're going to go about finding this distance x between point A and point C at the end of the second bar. This point is going to be useful for us because it's going to tell us the length of the moment arm. That's the normal force between these two bars. So we're going to go about finding x by setting up a series of similar triangles. The first triangle is this smaller one here, and we're going to use this angle phi to find this vertical length here. So we're going to do L times the sine of phi. This is the opposite to that angle phi. So we're going to do L sine phi to find the length of this line. And then we're going to use the angle theta back here to do the same thing. 4L times the sine of theta will get us this distance here. And then we're going to go, since this line is contiguous and this line is contiguous, we can set up a relationship between x and 4L and between L sine phi and 4L sine theta. That relationship is given here in this equation, so solving this will get us x equals L sine phi over sine theta. So the first thing that we have to do here in order to find this normal force C is to resolve all of our forces into components that are perpendicular to our moment arm axis, which is along the length of this bar. And so the normal force is already perpendicular, so we don't need to do anything to that. And then we have to make P, which is acting currently horizontally, into a perpendicular component to the bar. And we're going to do that by extending an axis, the axis of the bar out, and since this angle down here is theta, and this angle here is also theta. And then what we can do is take the sine of that angle and P sine theta, and that will be our perpendicular component of P to our moment arm. So then what we can do is we can write some of the moments equation, and that's going to look like some of the moments about A is going to be equal to 0, and from that we're going to do moment arm x times the normal force C. That's going to be a positive moment since it's acting in a counterclockwise direction. And then P sine theta over here is going to be a negative moment, so negative times the moment arm of 4L times P sine theta. So what we're trying to do here is solve for the normal force C so that we can apply it to the other arm, CD, and find the moment M in terms of P. So the equation that we have is this force here is going to be equal to this force up here. So let's solve for NC. X NC equals 4LP sine theta over X. And we can substitute in for X right now. X is going to be equal to L sine of phi over sine theta. We found that just a moment ago. So we'll substitute that one in, and we'll find that the normal force C equals 4LP sine theta times the inverse of X here, which is going to be sine theta over L sine phi. And then simplifying this, we will get that the normal force equals 4 times p times the sine squared of theta over sine of phi.
Alright, here we're explaining how to find the angle between the normal force coming off the bar and this lower bar here. As you can see, the bottom angle here is theta. If you come through, you can do the geometry and find out that this right here between the normal force and the vertical, the absolute vertical on an xy coordinate system, is the same angle theta. So we have that. So you can see that this normal force comes down here and the bar is here. We're trying to find the angle between them. This bottom angle here between the smaller bar and the horizontal is phi as a given. So you can bring that up here along the vertical and find this is 90 minus phi, as this is a right triangle. And because this is another line that's perpendicular to this line here, you can find that because this is 90 minus phi, this becomes phi. And taking vertical angles, you can come across and find this here is phi. So then this angle inside of here becomes phi minus theta, as given here.
Good job. So now that we've found the angle between this normal force and the perpendicular component of the bar, we can now write some of the moments equation to finally solve this problem. So what we're going to do is we're going to do the sum of the moments around D is going to be equal to 0, and that's going to equal the positive moment m minus this negative normal force C at a distance of L times the cosine of phi minus theta. So now after this we can just solve our equation. So m is going to be equal to normal force C times L cosine phi minus theta. And then we're just going to bring in the equation that we had for normal force from the other page. So the normal force was equal to 4 times p times the sine squared of theta over the sine of phi. So bringing that into here, we will have 4 LP sine squared of theta over sine of phi times the cosine of phi minus theta, and that equals to m, and we've solved the problem.